only going to be as exciting as they are. So, you know, there's not going to be any like theatrics or anything like that if you're not into science and astronomy, if you're not into just learning the quirky things of the universe, or how to apply things we learn in physics to cognitive health, then this is probably the wrong place. This is a place for nerds, basically, I think. There's two concepts I want to get into today, but this is all regarding thermodynamics. You're probably saying, well, how does thermodynamics, how does heat transfer explain a lot of things in physics? But it actually really does. Two things just to note. The Big Bang, we know 13.8 billion years ago, and everything's expanding, okay? And when you go really far out, it's exponential. Like when you go out, it's inverse. As the further you go out, the faster the expansion goes. So it's one of those things where like they can actually see some stuff moving away at what looks like light speed. And of course, local gravitation keeps things together. But quasars, we talked about the quasar that's billions of light years away. The M87, the picture you always see with the black hole with the gold around it, and you see the black, you know, from the Event Horizon Telescope. That's M87. That's the one. Usually you'll see the picture of M87 and it shows the big long jet. And I've actually taken that picture and taken quite a bit of light out of it to try to expose what's going on inside. Most of the Hubble pictures that I get, or even James Webb infrared ones, when I try to study the cores of these, it's just that the time scales are so small compared to, because you're using EMF to take a picture, and these regions actually, there's no EMF activity in those areas, so you can't like shine the light off a black hole and go, ah, there it is, because it'll just steal your light. But this one quasar, AMP08279, all right, this thing is really interesting. You know, we have water on the Earth. Well, this thing is 12 billion light years away, and it is creating perhaps a couple 100 trillion times the amount of water that we see on Earth. And it's really interesting the way that it does it. It's not like a black hole just doesn't suck in a bunch of stuff and just spit out water. But what happens is, if you think of a black hole as a motor, right? Just think of it as a cosmic motor. And it is okay to think of it that way. A motor could drive up a lot of energy, right? So basically this thing is the right kind of stirrer, okay, that can bring hydrogen from the Big Bang, oxygen from dying stars, perhaps, into the same area. By stirring everything up, it brings things into contact. Now, when you have that level of collision and you have that amount of stuff, a lot of times with that you get photons, you get heat, you get light from that heat, and then those can be separated. But what ends up happening is all this energy that gets driven up from this stirring can then power changes that happen. So for instance, like you might have hydrogen and oxygen there, and now you have all this extra energy around. So now the universe is going to take advantage of that, and you're going to get H2O. It's not the kind of water like, you know, you'd wade through or swish through and it's cool and all that, like what we experience down here. This would be really like supercritical states of water, like, you know, vapor, things like that, like superheated, you know, because it's extremely high energy stuff. But there's actually 140 trillion times what we have on Earth worth of water there. And it's funny because this thing is, you know, it's only so far away, but with the expansion of the universe, it's further away than you'd think it would be. So it's actually 23 billion light years out. And we know, the universe is only supposed to go back 13.8, so like there's something missing there. Well, there's been a crap ton of expansion, which is how that can be that way. But yeah, just to wrap it up, the easiest way to look at this is the black hole is your stirrer, okay? And so that's going to bring your oxygen from your star remnants, perhaps, or wherever that pops up. And it's going to bring your hydrogen together. And now it also provides the energy level because of bringing everything together. That added energy that's going to take place is now going to foster or give power to those particles to say aha and come together. So that's today's video. Hope you liked it. We're going to get into Hawking radiation